What if the most reliable marine engines ever built didn't come from the era of CAD software, digital sensors, or computer-controlled injection, but from the 1960s? It sounds like nostalgia talking, until you look at the evidence. Today we're looking at 5 engines from that era that refuse to die, and why many boaters trust them more than anything built in the decades since. Let's take a closer look. The Yamaha P7, when simplicity became the smartest choice. In 1960, the Yamaha P7 was the little outboard that launched Yamaha's entire marine business. This was a compact air-cooled 2-stroke single-cylinder unit displacing 123 cubic centimeters and producing roughly 7 horsepower. That's tiny by modern standards. You can buy a trolling motor with more thrust. But the P7, introduced in 1960, demonstrates a design truth that modern engineers sometimes overlook. Simplicity scaled to a purpose beats complexity every time. The P7 used motorcycle-derived architecture, which makes sense because Yamaha was already building motorcycles and had that expertise in-house. Single-cylinder, air-cooled, simple carburetor, points ignition. The entire engine had maybe 20 moving parts. There was nothing to fail because there was nothing there. No electronics, no sensors, no computers making decisions, just mechanical components doing mechanical jobs. What makes this relevant today comes down to serviceability. When a P7 stops running, you can diagnose the problem with basic tools and fix it with parts you can see and touch. Is the carburetor dirty? Clean it. Points worn? Replace them. Spark plug fouled? Swap it. Every component is accessible, understandable, and fixable. That practical serviceability is why many of these early machines are still repairable and show up in vintage running collections today, 60+ years after they were built. Compare that to a modern outboard with electronic fuel injection, computer-controlled ignition, and proprietary engine management. When something goes wrong, you need diagnostic software to read the fault codes. You need specialized tools to access sealed components. You need parts from the manufacturer because nothing is standardized. And if that manufacturer stops supporting your engine model, you might own a boat with a motor that becomes unrepairable, not because anything is mechanically broken, but because the electronics are no longer supported. P7 shows us what we traded away when we embraced complexity. We gained power density and emissions compliance, but we lost the ability to fix things ourselves. We gained computer optimization, but we lost mechanical transparency. For a small boat operating in remote areas, that trade might not be worth it. A 7-horsepower P7 that can be fixed with a screwdriver and pliers might be smarter than a 50-horsepower modern outboard that needs a dealer service department. Let's talk about the cast iron that refuses to die. Fast forward to 1964, the Perkins 4.236 introduced the compact cast iron workhorse that became ubiquitous across tractors, generators, and marine conversions. This is a simple, low-revving, direct injection diesel straight 4 built for longevity and field repairability. Perkins produced these engines in huge volumes through the 1960s and 1970s, and many are still running today. The 4.236's strength lies in its deliberate simplicity. Mechanical injection, no fragile electronics, heavy castings that can take abuse, proven parts interchangeability across applications. The engine was designed to run at low RPM for long hours, which keeps stress levels manageable and extends component life. Maximum RPM might be 2500, and cruising RPM sits around 1800. At those speeds, everything lasts longer. Modern high-tech diesels trade some of that durability for emissions compliance, power density, and electronic controls. Common rail injection gives you better fuel economy and cleaner combustion, but it requires high-pressure pumps, precise injectors, and computer management. When those systems work, they're impressive. When they fail, they're expensive and often difficult to repair outside of specialized facilities. The 4.236's mechanics are easy to understand, patch, and rebuild anywhere in the world. You can take one apart with basic hand tools. The injection pump is mechanical and rebuildable. The head can be removed and resurfaced. Pistons, rings and bearings are standard sizes available from multiple suppliers. This keeps the 4.236 competitive against more sophisticated engines that might have better specifications but worse serviceability. There's a reason cruising sailors love the 4.236. When you're in the middle of the ocean or anchored off a remote island, sophisticated electronics become a liability. You can't download software updates. You can't order proprietary sensors. You need an engine you can maintain and repair with what you have on board. The 4.236 delivers that. Its mechanical simplicity becomes a massive advantage when the nearest dealer is 1,000 miles away. Now to the Perkins 6.354 with big lungs but the same philosophy. The Perkins 6.354, designed late 1950s, production began early 1960s, took the same philosophy as the 4.236 and scaled it up. 6 cylinders instead of 4. More displacement, more power. But the same fundamental approach: overbuilt components, conservative power ratings, and modular serviceability. Perkins' own history calls the 6.354 the making of a legend in the 1960s, and that reputation was earned through decades of reliable service. Like the 4.236, the 6.354 favours durability over power density. The engine is heavy for its output, but that mass is distributed through thick castings and robust internal components. Crankshafts are sized larger than necessary. Connecting rods are built to handle more stress than they'll ever see. Cylinder walls are thick enough to be bored multiple times during rebuilds. These design choices create an engine that can run for thousands of hours between major interventions. In heavy commercial and marine use, those traits trump modern gains in power density. A modern diesel might make twice the horsepower from the same displacement, but it does so by running higher cylinder pressures, tighter tolerances, and more sophisticated fuel delivery. When everything works perfectly, that's great. But perfect conditions don't exist in the real world. Dirty fuel, missed oil changes, operating in extreme heat or cold. The 6.354's overbuilt design creates margins that tolerate imperfection. Modern engines optimized for peak performance often have no such margins. The 6.354's industrial DNA makes it safer, easier to maintain, and often cheaper to keep going than modern alternatives. Parts remain available because so many were built and because components interchange across applications. A rebuild kit for a 6.354 costs a fraction of what you'd pay for high-pressure common rail injectors on a modern diesel. That economic reality matters for operators who need to control long-term costs. Before the modern era, there was an engine whose entire system was an innovation. In the early 1960s, Volvo Penta launched key marine platforms that brought automotive and industrial engineering to boating. The MD diesel family and the AQ petrol inboard or outdrive combinations represented system-level thinking about marine propulsion. They were integrated solutions addressing the specific challenges of marine environments. Volvo Penta's early marine diesels prioritized closed cooling, which protects the engine block and head from saltwater exposure. Raw water cooling systems corrode internal passages and limit engine life. Closed cooling uses a heat exchanger to separate raw water from the coolant circulating through the engine. This one design choice dramatically extends service life in saltwater applications. The MD series also incorporated marine-specific corrosion protection. Sacrificial anodes are placed strategically, are corrosion-resistant, materials in critical areas, sealed electrical components. These seem obvious now, but in the 1960s, they represented a thoughtful adaptation of automotive technology to marine use. Many engine manufacturers just bolted marine accessories onto automotive blocks and called it done. Volvo actually engineered for the environment. The AQ drive systems integrated the engine with stern drive technology, creating a package that was more efficient and more reliable than traditional inboard shaft installations for smaller boats. The system-level approach meant the engine, transmission, and drive were designed to work together, rather than being separate components forced to cooperate. Why does this still outsmart modern tech? Because system-level thinking solves problems that component-level optimization creates. Modern engines focus on peak power and emissions compliance at the component level, but they don't always consider how those components interact with the harsh marine environment. Volvo's MD-AQ-era engines show how thinking about the complete system, engine plus drive plus cooling plus corrosion protection, gives you decades of proven, low-failure operation. That integrated reliability beats having the most powerful engine if that engine fails early due to corrosion or cooling problems, when rebuildability became legendary. The Detroit Diesel 71 series engines were already veterans by the 1960s, but they ruled that decade. These are two-stroke diesels, an unusual architecture that uses forced induction to scavenge exhaust and draw in fresh air. The Series 71 became famous for its rebuildability, replaceable cylinder liners, individual cylinder heads that could be removed without disturbing adjacent cylinders, modular design that made major overhauls straightforward. The Series 71's design prioritized interchangeability and ease of overhaul. That two-stroke diesel architecture and modular head design make huge rebuild cycles practical. When a cylinder wears out, you replace the liner and piston assembly. When a head cracks, you unbolt it and install a new one, built multiple times, with each rebuild returning it to near original performance. Modern engines often embed functionality in electronics and unique parts, integrated components that can't be separated, proprietary sensors that must come from the manufacturer, software-locked engine management that prevents aftermarket repairs. The Series 71 wins on raw maintainability. When something fails, a competent diesel shop can rebuild it even where modern electronics would be a showstopper. There's a reason you still see Series 71 engines in commercial fishing boats and workboats 50 years after they were built. These operations can't afford downtime, and they can't afford engines that become unrepairable when parts are discontinued. The Series 71's modular architecture means parts can be manufactured by aftermarket suppliers. The mechanical simplicity means repairs don't require proprietary diagnostic equipment. For operators who need maximum uptime over decades of service, that's smarter than any amount of computerized optimization. So, what did we lose in the name of progress? Look at these 5 engines and you see common themes: mechanical simplicity, heavy construction, conservative power ratings, modular design, rebuildability, field serviceability. These were design priorities in the 1960s because they had to be. Electronics weren't available to compensate for design weaknesses. You couldn't use computer control to make a marginal design work. You had to build something mechanically sound from the ground up. Modern engines reverse those priorities. We chase power density, getting maximum horsepower from minimum displacement. We pursue emissions compliance through complex after-treatment systems. We optimize fuel delivery with computer-controlled common rail injection. We monitor everything with sensors feeding data to engine management systems. These advances bring real benefits: cleaner emissions, better fuel economy, more power from smaller packages, but they come at a cost that doesn't show up in the specifications: complexity, fragility, dependence on electronics and software, reduced serviceability, shorter effective lifespans because engines become obsolete when parts are discontinued or software support ends. For recreational boaters operating near dealers and service networks, these costs might be acceptable. For commercial operators, cruising sailors, or anyone operating in remote areas, they're often deal breakers. The 1960s engines we've examined still outsmart modern technology in specific contexts because they prioritize different metrics. Not peak power, not minimum emissions, but with maximum reliability, serviceability, and longevity. When you need an engine that will run for decades with minimal support infrastructure, 1960s design philosophy delivers advantages that modern technology hasn't replicated. So, what does it mean for boat owners today? If you're choosing a marine engine today, understanding this history matters. You need to match the engine to your use case and support situation. If you're operating near civilization with access to dealers and service networks, Modern engines make sense. The technology works when you have the infrastructure to support it. But if you're cruising long distances, operating commercially in remote areas, or planning to keep your boat for decades, the 1960s approach has merit. Choose mechanical simplicity over electronic complexity when possible. Prioritize serviceability over peak performance. Look for engines with long parts availability and aftermarket support. Accept lower power density in exchange for better durability. Some modern manufacturers still build engines with this philosophy. Beta Marine is using Kubota industrial blocks. Northern Lights uses Lugger industrial diesels. These companies understand that not everyone wants or needs the latest high-tech solution. Some operators need engines built the old way, with old priorities, because those priorities still matter. So, the 1960s engines we've examined represent a different engineering approach. Not better or worse universally, but better in specific contexts where reliability and serviceability matter more than specifications. They show us what's possible when you prioritize longevity over power density, mechanical simplicity over electronic sophistication, and field repairability over factory optimization. What's the oldest engine you've run? Let us know in the comments. Real-world experience helps everyone understand what actually lasts. Thanks for watching.